continued development of total nitrogen deposition budgets in the U.S. This is our 6th session, and we have talks scheduled going through August of this year. Our first talk today is by Donna Schwede on modeling fluxes of reactive nitrogen using chemical transport models. And our second talk is John Walker on the topic of assessing uncertainty and total nitrogen deposition estimates for North American critical loads and applications. If everyone's ready to start, I'll go ahead and hand it over to you, Donna.
Okay, thanks, Christy.
Yep.
Okay, so thanks everybody for joining us today. As Christy said, I'm going to be talking about the chapter on modeling fluxes of reactive nitrogen using chemical transport models. This was a chapter that was put together with Havilah Pai, Rick Saylor, and Leiming Zhang, and most recently, at least for this presentation, Kathleen Fahey from my group has also contributed. So I want to acknowledge all of them and their part in pulling all this together. Let's see if I can get my slides to advance. There we go. Just by way of setting the stage for things, I wanted to share this cartoon of that we use on the Cmac webpage to kind of say, this is kind of the world we're trying to model. And just understanding the complexities of everything that has to go into an air quality model, from the different range of different source categories to the different processes that happen on a meteorological basis, to the different chemistry and transport that happens in the model, and fate. And so each part of that process has some uncertainties associated with it. And sometimes I think when I look at this picture, I'm amazed that we get it right at all. But we do. And but when it comes to like some of the uncertainties, I'm going to leave that for John to talk about next. I'm going to look at kind of a simplified view of things, and that would be on this next slide, where I've kind of taken the more complicated cartoon and kind of boiled things down a little bit into sort of the meteorological model, the emissions, the chemical transport model. So we have, oops, I did not want to do that. So in terms of our meteorological model, which you can think of as an example, the weather research and forecasting model, which is used a lot to drive Cmac and Cmac. You know, that's going to take in things like land use, boundary conditions, initial conditions. It can take observed data if you want to do some nudging. And the meteorological model is where a lot of the physics, the radiation, the microphysics, the dynamics happens. And then that produces a MET file, which goes into the chemical transport model. Now, the chemical transport model also needs information on initial conditions and boundary conditions and emissions. And then in the chemical transport model, you have the processes like vertical diffusion, advection, cloud processes, gas phase chemistry, aerosol chemistry, and air surface exchange. And then we end up with concentration and deposition being predicted by the model. And sometimes we can link the meteorological model with the chemical transport model and feed some of that concentration information back to the meteorological model and get an aerosol feedback, for example. Today, just to try to keep it, I mean, to talk about this whole concept could take like an entire semester, right, of a college course. So we tried to boil things down in this chapter and focus a little bit more sort of on the gas phase chemistry cloud portion of wet deposition, some aerosol chemistry, and the air surface exchange. So I'm going to start with atmospheric chemistry and start with the oxidized nitrogen system, which we've got a schematic here that was adapted from Seinfeld and Pandas, with the different species listed on the right, so that you can see sort of the interconnected nature of the atmospheric chemistry system and how compounds transform from one into another, either from oxidation reactions, from photolysis, and the different things that play into it. You can also see in the color coding that there's a range of solubilities which plays into the role that these different chemicals have. It's a very complicated system to get right from a chemistry standpoint, and I won't say that we have that right already. There are certainly some areas that we will continue to be working on for years to come. And just to kind of highlight some of these things in terms of what's important in the nitrogen budget, of course, organic nitrate chemistry is one that we've been focused on a lot, and we know that it is uncertain. The organic nitrogen species, so from the previous figure, PAN, NTR is what we call them in the Cmac model. That really includes a lot of different species. And if you look across the organic nitrogen species, there's a very wide range of solubilities and a wide range of volatilities. But what we try to do in the modeling, because if we tried to run every individual chemical reaction, the models would take too long to run. So we tend to group, sometimes condense the chemical mechanism down and treat groups of compounds as individual compounds. In the early days of Cmac, for example, we had one organic nitrogen compound, NTR, and it had a very low Henry's law. It wasn't very soluble, and it was not very representative of the suite of different organic nitrogen species that actually have Henry's laws that range over orders of magnitude. And so we have in more recent versions of the different chemical mechanisms that drive the chemical transport models, you have different ways that those surrogate species or ways that the organic nitrogen compounds have been grouped together for the modeling. And kind of what we really need is you really need to start out with a very detailed chemical mechanism and really get to understand the different organic nitrogen structures and then condense it back down. And that process of coming up with all the detailed mechanism is really what's needed, is to kind of really flesh out what is the complete world of organic nitrogen species and then condense it down. You have to remember that a lot of the chemical transport models were focused around ozone and SO2, and nitrogen species were kind of a throwaway. They didn't really keep track of nitrogen so much. So the idea that we need these detailed chemical mechanisms that really fully explore the organic nitrogen is a more recent phenomenon. For organic nitrates, the fate of those includes photolysis, deposition, oxidation, partitioning to the particulate phase, or hydrolysis. So these are really important because photolysis converts the nitrogen back to NOx, and hydrolysis results in nitric acid. Nitric acid, we know, deposits very quickly, and it's a big component of the total nitrogen deposition budget. And so we want to keep track of that. And I did just see a message from Doug asking about what chapter I'm talking about. Of course, this is a chapter from the Total Deposition white paper, and I forget which section this one is. This is section, do you remember, Christy? Yes, 3.2.3 of the Tdep white paper is where you can find more of the detailed information, and then I'm just going to cover the highlights here. All right, so again, we've got a lot of chemistry that's going on with organic nitrogen compounds. The photolysis converts nitrogen back to NOx. Hydrolysis results in nitric acid. We've got a lot of recent work on the hydrolysis lately that's looking at the role of organic nitrates and their contribution to SOA formation. And then the rapid conversion to nitric acid via heterogeneous hydrolysis. And I've listed a couple papers there, and Havel Pai in our group is somebody who's got a lot of experience in this group and does a lot of work on this. What we need is more experimental work to really understand organic nitrogen chemistry. and certainly measurements of organic nitrogen in the environment and fluxes will be really important. Let's see. Why? Okay, there we go. Okay, so a couple other concepts to talk about in terms of the atmospheric chemistry of NOI. Gas particle partitioning is really important. Organic nitrates and total inorganic nitrate can be either in the gas phase or the particle phase, and that's going to depend on your vapor pressure, your solubility, and the reactivity of the species. And the deposition velocity is going to be very different for something that's in a gas phase or a particle phase. So it's important to get it right to get our nitrogen deposition budget correct. Also, phase partitioning of inorganic nitrates is typically determined by a thermodynamic model within the chemical transport model. For example, Cmac uses isoropia. There are other thermodynamic models that can be used, but that's just one we use. But the thermodynamic model uses cation concentrations, and those have a pretty high uncertainty in models. You need a good dust model that will generate some of the cation concentrations. Some of them come from other emission sources, and the speciation of the dust emissions is something that's not well characterized necessarily in the models. And we see that when we do the measurement model fusion for Tdep, where we're trying to match up the cation concentrations from the model with the measured values. So that's an area that we could definitely use more measurements on and continue to improve, particularly our dust models that would help with that phase partitioning. N2O5 hydrolysis to nitric acid is another area of importance, and also one that is also an area of research that we are continuing to look at. So in the winter, N2O5 hydrolyzes to nitric acid, and that controls the lifetime of NOx. But the parameters that are currently in use by chemical transport models don't always get that right. It seems like since I've been at EPA, they're always looking at the gamma for N2O5, the parameter that predicts the conversion. And so there's still a lot of uncertainty there, and more is needed in terms of the experimental work. N2O5 doesn't tend to be as much a big part of the budget, but nitric acid is important. So anything that we are looking at that's converting to nitric acid, that does become an important topic for understanding the budget. Emissions, always a problem. This isn't really atmospheric chemistry per se, but it's hard to know if you've got the NOx, the oxidized nitrogen chemistry correct if you don't have good emissions, because then when you look at your results in the model, then it looks like if you don't have good agreement in your NOI, in your budget, when you get to the end, then if you don't have good emissions going in, then it's hard to tell if you've got the chemistry right. So that's been a problem. That's something that's been looked at, and there have been a couple of papers on that say that the NOx emissions, particularly from the mobile sector, may be overestimated. And I know they are working on the MOVES model in that area. But and that's just kind of an example of a confounding thing where your chemistry might be right and the emissions are making the model look wrong, or if your emissions are, so vice versa. I don't want to belabor that point. Okay, let's move on to reduced nitrogen. So I'm splitting this into ammonia and amines. We know certainly more about ammonia than we do about amines at this point, but even that's, the ammonia piece is still very uncertain. So ammonia can partition to the particle phase as ammonium, and so that has implications for particulate acidity and nitrate partitioning, as well as, again, deposition is going to differ if you're in the gas phase or the aerosol phase. The models do a pretty good job with the partitioning, so that's not as much of an area of concern with us, but we still have this problem with having the cations that can displace ammonium from a particle, so we still need these improved estimates of cations from the models. Of course, we know that ammonia emissions are uncertain, especially from animal feeding operations, because this is not a controlled sector of emissions. We don't have great reporting on it, and so the animal feeding operations are very uncertain. That adds to a lot of uncertainties in the emissions. And of course, ammonia exchanges bidirectionally with the surface. So if the ammonia concentration is higher in the atmosphere than it is in the surface, you'll have deposition. And if it's higher in the surface relative to the atmosphere, you'll have emission. Modeling that bidirectionality is challenging. You need to know what the emission potential is of the surfaces. And that's where the work that's being done with the Amines spatial variability study is going to be really helpful, because that's helping to build information on the different emission potentials of surfaces. And that's critical that continues to help our predictions of ammonia. Amines are really not well represented in models, but we know that they're important. They can contribute to PM 2.5 and they can contribute to nucleation events. We know a little bit about the emissions in terms of they can be emitted from animal husbandry operations or industrial processes and wildland fires, but those emissions are not very well characterized. We know they can react in the atmosphere with nitric acid and sulfuric acid and form salts. Again, not very well characterized in the models. We just need a lot more work in this area on the emissions and in the chemical mechanisms. And I think we don't even really have a very good idea right now of what's the how important those are to the budget. So that's an area for further research. Let's move on from atmospheric chemistry to air surface exchange. And so this is near and dear to my heart here. So most models are going to use the resistance paradigm in calculating air surface exchange. And I've shown a figure adapted from the Nemitz model, which shows the potential for bidirectional exchange of materials between the surface and between the air and the surface. So when it comes to modeling air surface exchange of gases, there are lots of differences between models in terms of the pathways that they use and how they treat the underlying structures. There are differences in the formulations of individual resistances. I would say that the non-stomatal pathways are particularly uncertain. You can measure the stomatal flux for water and scale accordingly. It's harder to measure what's the conductance to a leaf cuticle or to the ground surface. And so those are areas where the models tend to have parameterizations in them that are not necessarily first principles. Surface wetness is important even in dry deposition because a wetted surface with a soluble compound is something we need to account for. And also want to bring up that parameter values and resistances vary by land use type. And a lot of times the modeling is on a grid basis, and how you go from those individual land use types to the grid basis can be very different between the models. Compounds such as ammonia, as I already mentioned, can exchange bidirectionally, depending on the emission potential relative to the concentration in the air. So if you look at the figure on the right, if your surface, if your emission potential is 0, then this structure collapses to a unidirectional flux. So the same figure kind of works for everything. It's just a matter of whether things are bidirectional depends on the endpoints and what the concentration is in the surfaces there. But basically, in our air surface exchange models, we're looking at an aerodynamic resistance, RA, which is your resistance to turbulence. You've got a near surface layer resistance, your laminar layer resistance, and then you've got resistances that go to the canopy or the surface to the canopy, either through the stomates or through the cuticles and to the ground. So that they all kind of have some arrangement of these resistances, and then it's just a difference for models. But so since the models have different structures for these things and whether they treat compounds as unidirectional or bidirectional and what pathways they have, which model you use will control what deposition value you get. Here's an example from Wu et al. Paper. So I think I saw Ziyong on the webinar here. It's a paper that we did for the Borden forest data. Now these plots are for ozone and SO2, and those are compounds that the models were developed for, right? A lot of effort in the early days because ozone and SO2 were the easiest things to measure, that the models were developed around those. And you can see across these different models that there's quite a bit of variability in the deposition velocity for ozone and for SO2. Oops, sorry. And there's also differences, of course, with hour of day and with the season. But I wanted to point out that we see such a wide range of deposition velocities, and if we think about this for nitrogen compounds, the variability is probably even greater. But I don't have plots for those right now. I did see someone say that they're having trouble with the audio. Is that a general problem? Or can you hear me okay? Sound check?
I can hear you fine.
Okay, all right, thank you, Mike.
I can hear you fine too.
Okay, good.
Good
Okay.
here.
I'm good too.
Okay, thank you. Okay, so we'll move on now to air surface exchange of aerosols. So similar to the gases, most models use a resistance paradigm, but a slightly different form. And the aerosol dry deposition velocity is typically much lower than gas deposition velocity. We talked about that earlier when it came to the gas particle partitioning and how important that was. The deposition velocity of aerosols is going to depend on the particle size, and there is a difference across models in how the particle size is specified. There are models that use a sectional model, so you have bins of different aerosol sizes. Cmac uses a modal distribution, so you have 3 different modes. You can have models that have very specific deposition, have very specific diameters for the particles. And all of that makes a difference in terms of what you get back for the deposition velocities for your different compounds, and to whether they treat them as, whether you were to get back just a general like sulfate value, or if you're getting sulfate for the fine mode versus the coarse mode. All of that is important. These different models differ in which exchange processes are included. So things like gravitational settling, Brownian diffusion, impaction, those are all pretty standard to include. The differences come in things like interception and phoretic effects and rebound. Some models include those and some don't. And of course, depending on which processes you include and what your parameterizations are for those processes, you'll get different results. Again, landscape heterogeneity is important. Your deposition velocity will vary by the surface characteristics, and edge effects can be important to consider, although we don't typically in the models. So when you come to, if you have the difference of, think of air moving from like a grassland into a forest, when it hits the edge of that forest, the aerodynamics change dramatically, and that has a big effect on the particle deposition. And I would say that large uncertainties remain, and flux studies are needed across all different types of land use, and we need size-specific deposition flux studies for aerosols. Here's a figure that right straight from the white paper that Rick Saylor had put together. So this shows you some differences in deposition velocity for a range of particle sizes for different models and different surfaces. And so you can see that there's still a lot of disagreement between the models in terms of what the deposition velocity should be for a particular diameter of a particle, and that there is considerable variability across the different surfaces. So again, still more work needed in this area, and certainly measurements to help support model development and evaluation are needed. Let's talk a little bit about wet deposition next. So this is kind of a somewhat complicated picture, but wet deposition is complicated. You do have, what I'm going to talk about here are things that happen within the cloud, so in-cloud scavenging, and there's a lot of aqueous chemistry that goes on in a cloud. And then there is the below cloud part where I keep wanting to point and it's clicking, sorry, where you can have scavenging below cloud as the rain falls and washes things out. So I'm going to divide those two processes up a little bit in the next couple slides. In cloud scavenging. So for gases, this is the mass transfer between the gas and the aqueous phase. So you can use a couple of different approaches on this. One is an instantaneous Henry's law equilibrium, and that's dependent on pH if the species dissociate. A more complete treatment is the kinetic mass transfer approach, and that one is considerably more computationally expensive, but gives you a better characterization of the aqueous chemistry. And it's important to think about that these aqueous reactions can transform species into more or less soluble species. And so understanding that chemistry is really important to getting at the total deposition. So any uncertainties in the chemistry that we have then goes into what's in the aqueous chemistry, and that results in uncertainties in our scavenging and deposition. Aerosols, the process there within the clouds is nucleation scavenging. So aerosols can be incorporated into cloud water when droplets form on them. Models, of course, differ in their treatment, just like they do for the gases in the in-cloud scavenging. Interstitial aerosol scavenging by droplets, not all models include that. That's just one example of a process that may or may not be included in a model. So the models really differ in how they treat these things. And then you've also got to consider that these in-cloud scavenging processes depend on the droplet size distribution and the concentration and the liquid water content, the aerosol size and composition. So that's a whole section of uncertainties itself there, getting all of that right in addition to the chemistry. So there's still a lot of work that is going on in this area, and it's an area that's a little bit harder to have measurements that help verify the models. Below cloud scavenging. Gases often, when we do below cloud scavenging, so this would be like a washout, the gases often use a scavenging coefficient approach. So typically we think that it's irreversible scavenging, so once it's into the water phase, it stays there. I don't know too many models that actually let it come back out of solubility, but I guess it could. Ideally, you'd want to incorporate information on droplet size distribution for the raindrops and pH and your precipitation type and intensity. Most models, you have rainfall rate to go on, and that's about it. And a paper by that Lei Ming was involved in looked at the effect of the precipitation type, rain or snow, and that's important to consider, and models have been slow to adopt that aspect as well. Aerosols, again, a scavenging coefficient approach. You can include aerosol drop coagulation. That gets a little bit more complex. Not a lot of models include that. Again, scavenging coefficients, you need information on aerosol and droplet size, precipitation rates, whether it's rain or snow, and a lot of models don't have that. Really could use more time resolved, speciated and or size resolved measurements to help us evaluate the models for this. And just wanted to show this graphic from Wang et al. 2010, which sort of gives you an idea of different rainfall rates in the different figures and aerosol diameters and scavenging coefficients for different calculations and measurements. And you can see that the models and the measurements are not agreeing all that well on what the scavenging coefficient should be. So there's still a lot of work to do in this area. And we'll just keep plugging away at it. I think we'll now move on to just sort of summarizing the future research needs, of which there are a lot. I've mentioned a lot of them as I've gone along, and probably at this point you're wondering if we know anything, but we do. And the models actually do a surprisingly good job, but there are a lot of opportunities for improvement. And so first of all, we need comprehensive flux studies over a wide range of surface types for both gases and particles. For multiple chemical species, and this will go a long ways to helping us with our model development and model evaluation. We need process level measurements to elucidate fundamental exchange processes, especially for things like the non-stomatal pathways. How can we get at that piece of information? It's important for a lot of the chemicals. We need long-term flux studies that allow model evaluation across multiple seasons, so that we get a range of different weather conditions and different emission scenarios, the multitude of factors that can come into play. We need continued development of databases of soil and vegetation emissions potential for a wide range of ecosystems. Some of this information exists for European ecosystems. We need it for ones in North America, and that will help benefit our ammonia modeling, our bidirectional ammonia flux modeling. We need continued work on our emission inventories always for both NOx and ammonia. We need updates to the representation of gas and particle phase chemistry of organic nitrogen species, along with additional measurement data to validate model parameterizations. We need to continue to work on our dust models so that we improve the non-volatile cation inputs to our thermodynamic models. And we need to have continued measurements of cations for model evaluation. Continuing to develop mechanisms of explicit organic nitrogen structures, and so that we can continue to understand the chemistry of the different organic end species. Amines, a big area of uncertainty. Anything we could find out about amines would be helpful, especially emissions, chemistry, flux studies. That would all be great. Field studies, particularly targeted toward aerosols, would be helpful. You saw the plots where there's still some real big discrepancies between the measurements and the models. And so we need to continue to work on that. And then finally, you know, a lot of times we can't necessarily get all of the model evaluation we need, but model intercomparison studies are also extremely helpful. And I think that that helps kind of bound the problem maybe for input to some of the critical loads calculations in terms of knowing maybe a little bit of what's the uncertainty, at least if you use different models. So things like ACME, the Air Quality Modeling Evaluation International Initiative, it's particularly phase 4 that's ongoing right now, is looking at deposition in particular. So we're drilling down, not only looking at the grid level deposition, but asking people to output by pathway. So we'll have the stomatal flux and the flux to the cuticles and the flux to the ground and different resistances, and really be able to drill down into the differences between these models, both on a basis of running them for the different domains for North America or Europe, but we also have an opportunity for people to do comparisons on a box model basis. And that work will be continuing over the next year. That was a lot of information. So if you have questions, please contact me. And I can't say that I'm the right person on all of those topics, but I can put you in touch with somebody who can probably answer your questions better than I can. But I will give it my best shot now if people have any questions. Stunned silence. Awesome.
Let's give them a moment to find the mute button.
Oh.
Thank you, Donna.
And I forgot, while people are finding the mute button, I didn't look to see who the attendees are, but I did want to acknowledge that not only would this normally be tax day today, but it is also our NADP coordinator's birthday. It's David Gay's birthday today. So if David's on, we want to wish David a happy birthday. Normally we would be at an some years we've been at an NADP meeting and been able to celebrate in person. But
Hey, Donna.
Hey, Donna.
Oh,
yeah.
This is Doug Burns. I wanted to ask you a question.
Okay.
I just saw a new paper that came out this week in Stoughton, and they were trying to model dry nitrogen deposition across eastern China, I think.
Mm-hmm.
And they compared Cmac, Orf-Chem, and EMEP. Does that sound EMEP? E-M-E-P?
Right.
3 different
That's
models.
European model.
And, and the results did differ. I think Cmac was intermediate between the 2 models, as I recall. But they said two of their key conclusions. One was that all the models underestimated reduced nitrogen deposition based on measurements they had. And the second thing they said is the biggest source of uncertainty was the deposition velocities are still the biggest source of uncertainty.
Yeah, so I haven't seen that paper, but and I don't know whether they ran a bidirectional model or not. But a lot of times, you know, because we don't know very much on the ammonia emissions, I think that they tend to be, the ammonia emissions are probably underestimated. We don't know where all of the animal feeding operations are. There's a lot of uncertainty in that sector in terms of the waste and all. And I wouldn't be surprised that that the models are under predicting that, because we just don't know what the emissions are. And whether, I think it would really depend on the compound that you're talking about to know whether the greatest uncertainty is the deposition velocity or the emissions.
Okay.
I think that's pretty variable across compounds. I think some things like a nitric acid deposition velocity, that one we know pretty well because it's just controlled by the aerodynamic resistance. But something like the air surface exchange of ammonia, where you have to account for the bidirectionality of it, sure, there's a lot of uncertainty there. So it's kind of variable, and whether like things like there are certain organic nitrogen species that are soluble and some that aren't, and that solubility plays into how they deposit, even for the dry deposition velocity.
Thanks.
Okay.
Is there another question for Donna?
Yeah, this is Jen Murphy. Donna, I was wondering, are you guys explicitly tracking amines in Cmac?
We don't do a lot with amines. I will say we are not at this point doing a lot with amines. I think that I don't even know this. They're not really well characterized in the emissions inventory, so it's not an area that we've spent a lot of time thinking about in the chemistry. And I don't know, as the chemical mechanisms really have a lot in them for amines. I will confess though that I have not done a deep dive into that area.
Okay, the reason I ask is we're set up with our wet chemical technique to measure them, and we typically don't see them above detection limit. And I've been trying to think about how to get that information out there in a useful way, because based on what we don't see, it seems like they're not important, but without a comparison, it's hard to know.
Yeah, I think that at least, and I would like, maybe if Brett's on, maybe Brett could talk about this, but I know that, Brett, you've expressed some concerns about the role of amines and that we aren't accounting for those. So do you have particular sources that you are focused on, Brett?
Well, you know, we had indirect measurements of amines using these chemiluminescence instruments and trying to subtract it out from the total nitrogen. And it seemed to be potentially associated with fire and then possibly front range activity, which we were attributing to agriculture. The things that we've done is that, you know, Jeff Collett or Katie went out there. They tried to actually measure them near the feeding lots and didn't see all that much. And then when we were doing an NHX study, we actually looked for amines as well, and it was never above detection limit. So these things are out there, but we haven't been able to find them with a direct measurement at appreciable levels.
So not a high priority then for us to go after in the grand scheme of things, it sounds like.
Well, you know, amines are kind of critical from a particle nucleation standpoint. So there's a lot of interest in research going on there. I think they play an important role in atmospheric chemistry and particle formation, but maybe not a significant contributor to deposition where we're looking.
Yeah, I guess it's going to be, if we can't really measure them, if we're not finding them in places, it's going to be hard to account for them.
Well, there's better techniques out there than what we were doing. Or more sensitive, I should say.
Yeah, this is John Walker. I'll just chime in and say I do think it's valuable to know what is not out there or is out there at very low concentrations, because we do see this big pool of organic nitrogen in the atmosphere, particularly bulk measurements of water-soluble organic nitrogen in aerosols and in precipitation. And there's been a lot of work over the years trying to figure out what's in there. And so to know that some of these amines are out there in very, very low concentrations and probably not making a large contribution to this big pool of organics is important in terms of the deposition question.
You know, John, you've been doing more of the chemiluminescence work, right? your group? So have
well, we're doing a little bit more of it now. Most recently, Eric Edgerton's group participated in a study with us in southwestern North Carolina, and he used a chemiluminescence technique to get at bulk organic nitrogen compounds in the gas phase. But we have not done that specifically in my group.
Okay. Well, if you get a hold of that data, you know what we had subtracted off everything we knew, and what was left we called reduced organic nitrogen, and it may very well have been. If you could do that, you could see if you're getting a signal there.
Yeah, that's a good point.
You know, the other thing about amines is that I think there's hundreds of them, or even more of these compounds. And when we were measuring, you know, we were looking at like methylamine, we were looking at like 3. So let me scale back my comment and just say that if amines are out there, they're not in appreciable amounts. They're not what we were measuring.
Yeah, we're looking for the small alkyl ones as well, and not seeing them, you know, above a part per trillion very often. So I agree with that, but I also agree there's a lot of amino acids and things like that, and probably in the precipitation that could be pretty significant.
Mm-hmm. Mm-hmm.
Yep.
Okay. Thanks, everyone. Thanks, Donna, for the presentation and the deep dive into the modeling world, and for everyone for the discussion. I think with that, we will move on to our next speaker. And if we get that pulled up, John Walker will be speaking next.
Sorry, there's a lot of people here. I got to find John.
What's that, Mike?
I said there were just a lot of people here. It took me a while to find you on the list. I got you.
All right. It looks like you are not yet seeing my presentation, but let me confirm that. Can you see my screen?
Yeah.
Yes.
I can see it. Yeah.
Okay, good. All right. Well, I'm going to just move on along here. We're a little bit behind, but I'm going to try not to run over time. Good afternoon, everybody, and thanks for sticking with us. I'm going to kind of expand on some of the things that Donna talked about in her presentation, further reviewing some specific aspects of uncertainty and deposition budgets. And then I'm going to spend a little bit of time talking about a new simple metric of uncertainty and how we've applied it to the Tdep total deposition estimates. I'd like to acknowledge my co-authors here. I think most of you are online: Mike Bell, Donna, Amanda Cole, Greg Beachley, Ziyong Wu, and Gary Lear, who recently retired, who many of you know, also contributed to this work as it appeared in the white paper and then our paper that we wrote for Science of the Total Environment. So in terms of motivation for better understanding uncertainty and total deposition that are used for critical load exceedances and critical load applications, determination of the amount of deposition in excess of the ecosystem critical load or the exceedance requires an estimate of total deposition. And this total deposition is typically derived from gridded chemical transport models, which we just heard about, or a combination of measurements and CTM output, which is known as measurement model fusion. And we're going to talk a little bit more about that later. And because this critical load exceedance is used to inform policy decisions, we need to know the uncertainty of both the critical load and the exceedance itself. And the deposition estimate that's used to evaluate a critical load can influence whether an exceedance is expected, and can therefore influence management or policy responses. And the important point here is that rigorous quantitative estimates of absolute uncertainty are really not yet available for the reactive nitrogen deposition budgets that we commonly use for North American ecosystem assessments. So continuing on with the motivation for this work, Here I'm showing you a map or a plot of the exceedance of the herbaceous richness critical load based on Tdep total nitrogen deposition averaged over 2013 to 2015. And these are critical load exceedances taken from Simkin et al. 2016. In the plot, what you see on the y-axis is the critical load exceedance itself, and then on the x-axis is the corresponding total deposition budget. And the colored values are sites that are within plus or minus 2 kilograms of the exceedance. So we're referring to these as near exceedance sites. So these negative values indicate near exceedances that are not currently assumed to be at risk, but would be if deposition were underpredicted, for example. These are the yellow and the green. And alternatively, the positive values are those sites currently deemed at risk or above the exceedance that might not be if deposition were overestimated. And this wide range of deposition over which we see these near exceedances really highlights that uncertainty is important at both high and low levels of deposition. But it's important to note that high deposition doesn't necessarily mean high uncertainty, which we'll discuss a little bit more later. But knowledge of whether the uncertainty of the exceedance is considered low or high can inform the level of confidence with which management actions could be taken. So for example, at a location where the critical load exceedance is large and the uncertainty in the deposition estimate or the exceedance is low, a land manager could be confident that implementing a strategy to meet a critical load is appropriate and will be effective. But on the other hand, knowing that the deposition at a near exceedance location is highly uncertain could be beneficial in developing research or monitoring strategies to improve deposition estimates and reduce uncertainties so that a policy for achieving a critical load might be more confidently implemented later on down the road. So knowing these relative uncertainties of the components of the deposition budget could also help us prioritize research and monitoring to address the most important and uncertain species, processes, or pathways in the deposition budget. So now we'll talk about some aspects of uncertainty. Some of these we heard in Donna's talk, and then we're going to talk about a few of these examples in a little bit more detail. So within the deposition budgets, there's obviously uncertainty in the measured component of the budget as well as the modeled component of the budget. And some of these uncertainties we know a lot about, and some of them we don't know much about at all. For example, there's uncertainty in our measurements of wet deposition, but we know those uncertainties from co-located comparisons and things like that. There's uncertainty in our air concentration measurements that are used in the bias adjustment of the measurement model fusion techniques, for example. And we know what some of these uncertainties are in a quantitative sense because we've done side-by-side comparisons. But some of the uncertainties that we don't know as much about include the completeness of the reactive nitrogen chemical budget. So are we measuring all of the important nitrogen species that make up the total nitrogen deposition budget? And with respect to things like organic nitrogen, we know that we're not, but we don't have a good handle on what these uncertainties are. There's also the issue of spatial and temporal representativeness of the measurements. Are they representative? These are issues when we scale up experiments, for example, that are conducted over short periods of time, or when we spatially scale measurements that are conducted in complex terrain. So there are issues there on the measurement side. And Donna really went into a lot of detail on some of the model uncertainties, but just to reiterate, completeness of the deposition budget is an issue there. The model is not representing all the important forms of nitrogen in the budget, but that is improving. There are uncertainties in the inputs of the emissions and the meteorology and the representation of the chemical reactions, as we heard. The deposition algorithms themselves, particularly dry deposition, are uncertain, and we're going to talk about that a little bit more. Spatial averaging of subgrid processes within the model. Spatial interpolation of wet deposition, and with respect to measurement model fusion, the way that we bias correct the model and the way that we spatially interpolate the results are sources of uncertainty. So as I said, over the next few slides, we'll talk about a few of these examples in a little bit more detail. On this next slide, we'll talk a little bit about the completeness of the deposition budget. So again, are we capturing all of the important forms of nitrogen in our total? To kind of guide this example, I'm showing you here a map of the percent of total nitrogen in the Tdep estimates that's contributed by what we're referring to as unmeasured species. And in this case, these are the species that are not monitored under the CASNet program, which is the primary data set that we use to bias correct air concentrations for dry deposition estimates in Cmac and in the Tdep process. And so what you're seeing here is the red areas are where these unmeasured species, specifically dry deposition of these species, contributes a lot to the total budget. And the blue areas are those areas where these unmeasured species contribute a small amount of the total. And in this case, the unmeasured species comprise nitric oxide, NO2, HONO, N2O5, and organic nitrogen. And it's the organics that I want to talk about a little bit on this slide. So to reiterate, in the Tdep process, the dry deposition of the unmeasured species is unadjusted Cmac output. For things like nitric acid, ammonium aerosol, nitrate aerosol, we bias correct the Cmac output using the CASNet observations, but that's not the case for what we're referring to as these unmeasured N species. This is just the Cmac output. And if you look at this averaged across the continental US, this group of unmeasured species contributes about 15% of the Tdep total nitrogen deposition. But we know, as Donna mentioned, that the organic nitrogen chemistry in Cmac, this was version 5.0.2 used for these maps, is incomplete. But we also mentioned that it's improving over time. But in this case, the organic nitrogen comprised peroxyacetyl nitrates, some aromatic pans, C3 and higher pans, and a handful of organic nitrates in the gas phase. And so because the organic nitrogen chemistry is incomplete, the dry deposition component of these unmeasured species is incomplete, underestimated. With respect to wet deposition, if you look globally at the wet deposition measurements, you'll see that on average about 25% of the water-soluble nitrogen in wet deposition is an organic of some kind. Wet deposition is also not well represented in this version of Cmac due to a limited range of solubilities for the organic nitrates. And in this case, wet deposition of organic nitrogen is not included in the total deposition estimate. So the take-home message here is that the organic nitrogen contribution to the total deposition budget is underestimated really by some unknown amount at this point. So that's an important uncertainty that we struggle with in the total nitrogen deposition budgets. So I next want to talk a little bit more about dry deposition algorithms. We know that if you look across the United States, dry deposition accounts for about half of the deposition budget compared to wet deposition on average, and of course it dominates the budget in more arid regions. So because we have this well-developed national monitoring network for wet deposition of inorganic nitrogen, we have a good feel for the magnitude and the variability of wet deposition. But that's not the case for dry deposition. Our measurements of dry deposition are much more limited, and our understanding of the deposition processes is more limited. So what I'm showing you here is an example of some work that was conducted by Chris Fletcher and his colleagues, and it's a really nice comparison of dry deposition models where they used data from the Nitro Europe study of 55 sites where they measured micrometeorology and air concentrations, and they used that data to drive these 4 dry deposition models for ammonia, nitric acid, NO2, and ammonium and nitrate aerosol. And what I'm showing you here are the deposition velocities for those 4 models across land use types. So for all of the sites that fall into a particular land use category here, these are the statistics of the model output. And what you can see is that there's a lot of variability among the models for all of the compounds, particularly for ammonia. And in some cases, the models may differ by a factor of 3 or more, even within single land use categories. So this really illustrates the uncertainty of the dry deposition models and our growing knowledge of the deposition processes, but we have a ways to go. And as Donna mentioned, particularly for things like ammonia, non-stomodal deposition processes are an area where we really need additional field data. For example, understanding deposition to the cuticle surface or wet surfaces. Those are difficult measurements. They require a lot of data to tease out those processes, and that's an area where we need more data for sure. So moving on to talk a little bit about measurement model fusion. These approaches, like Tdep, are becoming more widely used for deposition assessments. And there are several sources of uncertainty in the MMF estimates of deposition, including the observational data that's used. For example, there can be temporal and spatial gaps. Different chemical transport models can be used, and those differ in terms of the processes that are represented. And in the fusion approach itself, the method of bias correcting the model output with observations and the spatial interpolation that's used. Adagio and Tdep are two examples of measurement model fusion techniques that have been used for North American deposition assessments. And they differ in some important ways. For example, Adagio uses ammonia observations from the Amines network, and Tdep doesn't do that yet. Adagio uses data from urban NO2 networks. Tdep does not do that yet either. They use different precipitation data, different chemical transport models, and the fusion procedures themselves are a little bit different. But what I wanted to emphasize here is that even with all of those differences, if you compare the approaches, and this is showing a comparison across North America, the agreement between the two approaches is really promising. They differ in some areas, but all in all, they show fairly good agreement. And I'll emphasize here that it's these comparisons of approaches and models that do help inform the uncertainty in the deposition budgets and the components of the deposition budget. So as Donna mentioned, more comparisons of models and deposition modeling approaches are really, really needed, but I wanted to highlight this example here. Spatial representativeness is another thing that we talked about a little bit, but I want to highlight that again here. Typical dry deposition output from chemical transport models is provided at the grid scale and is obtained by averaging subgrid variability in either the surface characteristics or the dry deposition velocities. So the model doesn't really spatially resolve the land use types within the model grid. It really has knowledge of the percentage coverage of the different land use types and differences in things like leaf area index, surface roughness, plant stem model responses. These all create subgrid variability in deposition velocities. And so this introduces some uncertainty when we want to take a grid average deposition value from a model and downscale it for a deposition assessment in a particular ecosystem. What I'm showing here is how different some of the grid cell averages can be versus land use specific deposition. And here I'm showing output from the surface tiled aerosol and gaseous exchange dry deposition option for Cmac version 5.3. So this stage option does give you land use specific fluxes. So Donna mentioned nitric acid earlier. It's a compound that we know a lot about compared to other nitrogen compounds in terms of the deposition processes. And we know it deposits rapidly to rough surfaces. So if you look on the upper right-hand plot, this is dry deposition of nitric acid at the grid cell. And then if you look over on the left-hand side, this is nitric acid to a deciduous forest within the grid cell. And you can really see some big differences in deposition where you have grid cells where forest coverage is patchy. And Donna and her colleagues and Fabian Paulo and his colleagues have done some good work looking at in more detail at the uncertainties of downscaling grid average fluxes to land use specific fluxes. Ammonia, as we mentioned, is another difficult one because the different land use types within a grid can have much different compensation points and emission potentials. So for example, if you have a grid where you have crops that have a very high nitrogen status mixed in with natural land use types like forests, you can see different magnitudes and even different directions of fluxes depending on land use type. So in those grids, you'll obviously get very different, or can get very different results at the grid cell versus land use specific. So those are just some examples here, and so where we need to move in the future is to have a land use specific option for measurement model fusion procedures. So that's kind of an overview of a few examples of uncertainties. And now I want to shift gears and talk a little bit about an approach that we're using where we've come up with a simple metric of uncertainty that can be used for deposition and critical load assessments. With all of these uncertainties that I've talked about and that Donna mentioned, where do we stand in terms of being able to quantify the absolute uncertainty and annual total deposition budgets? And we'll take the Tdep measurement model fusion approach as an example. So if we just ignore the problem of downscaling from the grid to the ecosystem, some aspects of uncertainty in the Tdep procedure include the measurements of the chemical concentrations in air and in precipitation, the spatial interpolation within the fusion procedure, the prism estimates of precipitation amount that are used for wet depositions, the Cmac concentration predictions for the unmeasured species, and the Cmac deposition velocities. And then, of course, the incompleteness of the budget is an issue that is difficult to get a handle on. But if you look at some of these, if you break down these elements of uncertainty, we do have quantitative estimates for some of these categories of uncertainty at the weekly time scale. For example, as I mentioned before, we have an idea of the uncertainty in the measurements of air concentration and wet deposition. We get estimates of uncertainty that come along with the prism estimates, and we can estimate uncertainty in spatial interpolation procedures. But we really don't have a handle on the uncertainties in the deposition velocities that we get out of chemical transport models. They can be informed by model comparisons, but we don't have a real rigorous estimate of uncertainty for that component. But once we do compile all of these different aspects of uncertainty that make up the total deposition budget, we're going to need methods for aggregating these component uncertainties within and across the chemical species and then up to the annual scale. And so we're moving in that direction with more rigorous model comparisons like Donna mentioned with the ACME work. But we're not quite there in terms of being able to piece together all of these aspects of uncertainty in a quantitative way to come up with an estimate of absolute uncertainty. So here I'm going to introduce a simpler metric of relative uncertainty based on our current understanding of deposition processes. And I'll walk you through the methodology, and then we'll talk about some examples. And here I'm talking about this new metric as we're applying it to the Tdep total deposition estimates. So we start off at each grid point by applying an uncertainty rating to each component of the total deposition estimate. And we're going to talk a little bit more about that in a minute. From there, we calculate the fraction of the total deposition at that grid point that's contributed by each component. And we then calculate the fractional deposition weighted uncertainty for each component using our uncertainty ratings. We sum the deposition weighted uncertainties up for each component, and then this gives us what we're referring to as the weighted deposition uncertainty metric for the total nitrogen deposition estimate. And I'll reiterate that this is a qualitative metric of relative uncertainty, and it's not an estimate of absolute uncertainty. So it's important to keep that in mind. So on the next slide here, this is the equation showing how we relate the fractional contribution of the component to the total deposition and the uncertainty rating for each component of the total deposition. And so now I want to walk you through how we establish these uncertainty ratings for the to 8 components of the total deposition budget. So to start off with, our knowledge of the magnitude and the spatiotemporal patterns of wet deposition of ammonium nitrate is certainly more complete than for the other components of the Tdep reactive nitrogen budget. So this metric of uncertainty is relative to wet deposition of nitrate and ammonium. We're assigning them an uncertainty rating of 1. We know more about them than any of the other components in terms of their uncertainties, and so 1 represents the lowest level of uncertainty. Now, the Tdep measurement model fusion does not include wet deposition of organic nitrogen. So to incorporate this aspect, we've defined a non-measured wet deposition variable, NOM-wet, which we assume to be the bulk organic fraction of wet nitrogen deposition. And as I mentioned earlier, based on global data, we're assuming that ammonium and nitrate wet deposition account for 75% of the total nitrogen wet deposition on average, and the organic fraction represents the balance. So because we neither measure nor model this in the Tdep procedure, we assign it the highest level of uncertainty, which is a rating of 5. Moving on to the dry deposition, it's important to remember that the estimates of Tdap dry deposition are derived from Cmac deposition velocities, and so they're just inherently going to be more uncertain than the wet deposition numbers. And remember that nitric acid, nitrate, and ammonium aerosol are bias corrected using CASNet measurements. Of the dry deposited species, our knowledge of nitric acid deposition is certainly more complete than for the other species. And this is reflected in the much higher level of agreement for nitric acid relative to the other compounds that we see in Chris Fletcher's study that I showed earlier, in which they compared dry deposition models using data across 55 sites. The deviation of the models was lowest for nitric acid. So here we're going to assign a rating of 2 for nitric acid dry deposition, reflecting more uncertainty than wet deposition, but the lowest degree of uncertainty for the dry deposited species. So we heard a little bit about particle dry deposition earlier. Our knowledge of particle dry deposition is less than nitric acid. As Donna showed, there are still some big differences in terms of model estimates of particle dry deposition depending on which model you use. But in this case, we are at least bias correcting the Cmac model output in terms of the air concentrations for nitrate and ammonium aerosol. So we give them an uncertainty rating of 3. They're more uncertain than nitric acid and wet deposition of inorganic nitrogen. And then we move on to ammonium, ammonia. As we heard earlier, this is the air surface exchange processes for ammonia are much more complex than for something like nitric acid. Another thing about ammonia is that it's not bias corrected in the Tdep procedure. And so we give it here a higher rating of uncertainty at 4. And we do the same for the unmeasured dry deposition species. Remember, this was NO, NO2, HONO, and the organics that are included in the model. So because we know the organic fraction is incomplete in terms of the dry deposition, but at least we do have some model estimate here for these, so we also assign them a rating of 4. So some important things to keep in mind about this metric. The value can range from 1 at locations where 100% of the deposition is contributed by components with a rating of 1, and 5 at locations where 100% of the budget is contributed by components with a rating of 5, which is again the highest rating for uncertainty. So there are some obvious simplifications and limitations here. One is this implied linear relationship between the uncertainties of the deposition components. In reality, wet deposition of organic nitrate may be much larger than a factor of 5 more uncertain than wet deposition of inorganic N, but we've made that simplification here. Another thing is that the uncertainty rating is a constant value. It's ignoring temporal and spatial variability, and we know there's greater uncertainty in deposition, both wet and dry in complex terrain. urban to rural gradients where things are changing rapidly in space. Phenology is important in terms of temporal behavior of dry deposition, phenology of vegetation, and the temporal patterns and air concentrations come into play. And we're ignoring that temporal variability there. So it's important to keep those in mind as we look at some examples of how we can apply this metric. So before we do that, I wanted to just show you this map of total Tdap in deposition for 2016. We'll refer back to this map, but I wanted you to get a feel for the range of total nitrogen deposition that we see across the U.S. from very low levels up to greater than 20 kilograms of N per hectare, and where some of the areas of highest deposition rates are, the central U.S. and Midwest associated with agricultural activities and ammonia emissions. You see a hot spot there in eastern North Carolina that's also agriculture related, but we also see urban areas as hot spots, reflecting the importance of NO2 and other inorganic oxidized nitrogen species. And we will refer back to this map. So this next map is if we take the 2016 Tdep map and calculate the weighted deposition uncertainty metric, this is what the spatial distribution looks like. So the red values represent the higher levels of uncertainty. These are the higher values for the uncertainty metric up to 3.8. And the green values are those areas where there's a lower value for the uncertainty metric, or a lower degree of uncertainty in the total deposition number. So you can see that the highest values of the metric occur in the Southwest, the California Central Valley, and east of the Cascade Mountains, where total deposition really is dominated by the dry deposition component, which is more uncertain. We see high values in eastern North Carolina and some areas of the Midwest that reflect a large contribution from ammonia dry deposition to the total budget and corresponding higher overall uncertainty. And again, we see higher values in and around urban areas in the Northeast US and cities like Atlanta, showing where NO2 dry deposition is important. And remember, this is one of the unmeasured species that's modeled in the Tdep estimate. And then we see lowest values occurring where wet deposition really dominates the budget. And I want to note here that areas of high deposition don't necessarily correspond to high uncertainty. If you look at this map and look at Nebraska, for example, there are areas of Nebraska that have a relatively low degree of uncertainty in terms of the weighted deposition uncertainty metric. But if we look back at this map, we can see that some areas of Nebraska really experience high rates of deposition. And this particular year, these areas really saw a lot of wet deposition of ammonium nitrogen. So that's an example where we have a high deposition rate and a relatively low degree of uncertainty because the budget is dominated by wet deposition, which is less uncertain. So this next slide is kind of a different way of looking at the uncertainty metric. Here we have calculated the percent contribution to the metric in the previous slide that's contributed by each of the deposition components. So now we've split them out individually and asked the question, what do they individually contribute to the total uncertainty in terms of a percent contribution? And what you can see, I've ordered these dry deposition in the first two rows and then wet deposition along the bottom. And then in order left to right of from increasing importance to least important. And what you can really see is that ammonia dry deposition and the uncertainty of ammonia dry deposition is really a big contributor across the U.S. And you can really see some similarity between the contribution of ammonia dry deposition to the total uncertainty here and the general patterns of uncertainty in terms of the value of the metric in the previous slide. So we see ammonia is important across the U.S. The non-measured species, again, we're seeing them show up as an important contributor to overall uncertainty in the eastern U.S., where we see 3.8 contributions of NO2 deposition to the total budget and inorganic oxidized nitrogen. In terms of wet deposition, we see wet deposition of organic nitrogen is an important aspect of uncertainty pretty much across the board. So this is really an area where we need to improve our understanding of the contribution of organics to total deposition. So again, just a different way of looking at the weighted deposition uncertainty metric. So I want to kind of wrap things up here. We only have a few more minutes, and I want to show an example of how the metric can be applied at the local scale. On the left of this slide is a map of the deposition uncertainty metric for the near exceedance sites that I showed back in slide 3, with an expanded view of the George Washington National Forest and the Shenandoah National Park. These two federal land units exist on opposite sides of the Shenandoah Valley. In this case, locations with the highest weighted deposition uncertainty values occur on the western slope of the Shenandoah and the eastern unit of the George Washington. And on the right-hand side of this slide, I'm breaking down the percent contribution of the individual deposition components to the total uncertainty, like we did in the previous slide, averaged over the near exceedance sites within each area, and then ranked from high to low. So if we take George Washington National Forest, it has about 62 of 431 sites that are near exceedance, so what we're referring to as near exceedance, plus or minus 2 kilograms per nitrogen per hectare per year, with an average of 1.4 kilograms below the critical load, or 12.5%. And here, wet deposition of organic nitrogen and dry deposition of the non-measured species, nitric acid and ammonia, contribute about equally to the total uncertainty across those sites. Comparing that to Shenandoah National Park, where the average deposition is about 0.5 kilograms per hectare per year below the critical load. And in both of these areas, the total deposition rates are on the order of about 8 to 10 kilograms of N per hectare per year, if I remember correctly. But in this case, we see ammonia contributing much more to the total uncertainty in Shenandoah, reflecting the contribution of ammonia from agricultural activities. So this is just an example to show you that based on the spatial distribution of these component uncertainties, you may, for example, prioritize monitoring and research activities around oxidized and organic nitrogen in George Washington National Forest, where you may prioritize more monitoring and research around ammonia in the Shenandoah National Park. A couple of examples, and we go into more case studies in our journal article if you want to take a look at that, and I'll give you the link a little bit later. So just to wrap up, we think this weighted deposition uncertainty metric is certainly just a step toward more rigorous estimates of absolute uncertainty, but it can be helpful at the local scale to identify the most uncertain deposition components, prioritize future research and monitoring activities, and guide more detailed investigations of uncertainties. When we apply the metric across the U.S., we see ammonia as an important source of uncertainty in many areas of the country. We see uncertainty in the dry deposition of oxidized N, particularly NO2, important over large areas of the eastern U.S. And so moving forward, this uncertainty metric is kind of akin to the reliability rating that's used for critical loads, where using the literature, you develop an estimate of reliability for the critical load. Is it reliable or not? And so this is kind of akin to that uncertainty rating. And maybe we need to consider an expression of the uncertainty metric that's more in line with the reliability assessment of critical loads. Maybe we, instead of a numerical value, should express this as lowest, intermediate, or highest uncertainty. And in the future, we want to try to incorporate a spatial component into the deposition uncertainty metric using GIS information like elevation, for example. And then very quickly, I know we're running out of time here. I'll recap some of the things that Donna said regarding priorities for addressing uncertainty and future research to reduce uncertainties in total deposition. Continuing to compile non-network deposition measurements for model evaluation, I think, is important. Incorporating other network and network data like our urban monitoring networks into the Tdep measurement model fusion process is important and something that could be done in the near term. Comparisons of deposition from measurement model fusion procedures and chemical transport models is ongoing and something that in the near term is going to continue to help us better understand uncertainties in total deposition. And then over the long term, I won't go through this whole list, but getting organic nitrogen measurements into our national monitoring networks, I think, is a high priority. Donna mentioned long-term measurements of dry deposition being important. I think land use specific deposition options for measurement model fusion is another high priority. Maybe that's something that could be done in the nearer term. And then again, ultimately, the goal is to develop maps of absolute uncertainty for critical load assessment. The critical loads community is going in that direction now. They have their own efforts to develop more rigorous estimates of uncertainty for the critical loads themselves. Here's a link to our journal article if you want to look at some of this information in more detail. And I will continue to kind of mold this metric and improve it in ways that are more useful to the critical loads community.
Thank you.
Okay, if there are no other questions for John, I would just like to thank our speakers again today. John, I believe you are officially off the hook for the remainder of these seminars, so congratulations on that.
All right, thank you.
Yeah. I do want to remind folks that the Tdep white paper is available on the NADP website. If you go to NADP and then the committees tab and then Tdep on the left navigation, you'll be able to find the paper as well as links to the Stoughton articles that came out of this paper, as well as the EM articles. I believe those PDFs are posted there. In addition, you can also find recordings of past webinars. So a lot of information available to you. As far as the schedule coming up, we will not be having this seminar in May, as we'll be meeting with the committee during that midweek of May. But we do have a very large audience today, and I would just like to let folks know that the Tdep Sub-Science Committee of NEDP is an open committee, and if folks are doing work that is applicable to the topics that we've been talking about, please feel free to join us, and you can do that by reaching out to me or your favorite NEDP contact to find out more information about that. The Tdep Science Committee meeting is on May 12th from 11 to 3:30 Eastern Time. And then we will reconvene these webinars in June, and it looks like the date is June 17th. And our two speakers in June will be Graham Sexton, who will be talking about snow and atmospheric deposition. Graham works for the USGS. And then also Greg Beachley from EPA on remote sensing measurements. I believe that's all I have for today, unless anyone has anything else. And hearing none, we just appreciate your participation today, and continue to stay safe and stay sane in this crazy world. We'll talk to you all soon. Thank you.
Thanks all. Talk to you soon.
Thank you.